repeat that quickly again. Right, I'll set this to record now. So we're now recording. Right, so we have our points here, and we draw our best fit line. This is called a best fit line, where we try to get most of our points on the line. Right, as the length increases, the period squared also increases. Right. Moving on, we this is actually this is the best fit line. This was generated by the computer, right? And we realized that these 2 points are essentially the same distance away from the graph, right? Now we move on to equation of a line, where this is the relationship between the y variable and the x variable. So the x variable is called the independent variable. What does this mean? It means that it doesn't depend, or it can act on its own, and then you will get a result from the y variable. So when we increase the length of our pendulum, we find that the period squared also increases. Right? That's simply what it means. This is just for information. When you actually going about doing your labs, you need to be able to identify your dependent and independent variable. Right? Now we move on to the gradient and the y-intercept. So the gradient is essentially um is essentially a number that represents the steepness and direction of a specific graph, right? So what does this mean? Um, as if the graph is more steep, if the graph is steeper, it will have a higher gradient. So just tell me, which one of these lines, you have line A and we have line B, which one of these lines would have a higher gradient?
A.
A would have a higher gradient, right? Because it is
A.
steeper. Simple. That's all it represents. Now we will talk about the y-intercept. The y-intercept is the point at which the graph crosses or intercepts the y-axis. So we have our graph here, and this is 0, 1, 2, 3. And our line, right? Our line crosses this line right here. What would be our y-intercept? What is the value of our y-intercept?
Sir, 1.
1 would be value of our y-intercept. So this, as I said, it's very easy. See, it didn't take us a minute to go through, right? So we have the gradient is represented by m, and we have a y-intercept represented by c. So in this case, c is equal to 1, right? In this particular case, because the graph cuts the line cuts the graph the y-axis at 1, right? All right, we'll move on now. Um, does uh, what's the difference between this graph and this graph right here? What is the difference? Are we
Sir,
seeing that?
they're closer together.
So these lines are closer together, right? Anything else as it regards to the axes? How the axes look? This axis and this axis right here.
One of them is started at 40.
Right. So we covered this in the last class, right? And we said that we can essentially cut the graph right here, right? Because we have no useful information here. This is just taking up space. So we cut the graph and we get a better line. We get a better distribution, right? And we did that in the last class. Now we'll move on to the gradient, right? We'll go ahead and calculate the gradient of this graph, the same graph over here. Now, when we're going to calculate our gradient, we need to take two, we need to take a point, we need to find a point between the first two values, and we need to find a point in between the last two values. So the first two values, our point would be around here, right? Somewhere in this region right here. And our last point is between the last two values. This is our point, right? And we're comparing these 2 points now for the gradient, the calculation of the gradient. Bear with me for a second. So the normal exercise is to match these to the particular axes, right? So we match them, right? And we match this also to find out the position of this point. And we do the same for down here, and we do the same for over here. And we draw a triangle essentially to connect them, right? So this is how we go about finding the gradient, right? This is 1.60. This is about 2.3. This is about 57 or so. It could also be 56 point something, but it's essentially 57.5 or so. And this is essentially I'm just estimating. So when we're calculating, it's mostly about estimate, right? Some students already did this, but I'm just going through, right, for the students who were not able to finish this, right? So this is about 40. This is 42.5 because in the middle of 40 and the middle of 45 we have 42.5. So this would be about 43, right? This would be about 43 right here. All right, so we're understanding.
Yes, sir.
Right, so we take 2 points and we find their positions. That's simple. We find 2 points between the first two and the last two, and we find their position. So this up here is our y2, and this down here is our y1. This is the second value on the graph, and this is the first value on the graph. While this is our x2, and this is our x1. So this is the second value on the x-axis, and this is the first value on the y-axis. Are we
Mr.
understanding? Go ahead.
Can you go over that what you just did, please?
The y2 and y1.
Yes, sir.
Right. So as I said, we took two values, random values, in between the first 2 points and the last 2 points to get a range of values, to get an understanding of the shape of the graph. That's the only way. We can't just take one of these points, because suppose we were supposed to take this point, it would be off the line and we would get a result for the gradient. But in order for us to get a range of values, we need to take the first value between the first 2 points and the last 2 points, right? And we basically match it up. We're trying to find the position of these 2 points. So we have this point here, and we have this point here, right? And we try and find the position. So we match this up to the y-axis, and we match the same value to the x-axis to find its position. And we call this one 0.2. This is our 0.2. And then we have 0.1 down here where we match this up to the y-axis and we match this up to the x-axis, right? And we basically have our point. So we'll compare these two and we will compare these two, right? So are we understanding a little better now?
Yes, sir.
Yes,
All
sir.
right, beautiful. Right, so we did the same thing, right? This is a little neater than what we just did a while ago, but we did this is essentially the same thing, right? And now we move over to the calculation, right? So the gradient, as we said, is a number that represents the steepness and direction of a specific graph. So we have our graph here, right? And we want to find the gradient A. We want to find the gradient of A, right? We would use this formula right here. Remember, we have y2, we have y1, and we have x2, and we have x1, right? So we have all the things that we need, right, from the previous thing that we just did a while ago, right? y2, y1, x2, x1. Beautiful. So we just plug in our values, right? Remember we said that the y2 is about 2.35, 2.4 thereabout, is just an estimate, right? And our y1 is about 160, right? So 2.35 here, right? This in the middle of 2.2 and 2.4 we have 2.3, so 2.35 would be around here. and we have our 1.60, right? This matches up. So we say y2, y1, right? And we get our values, and then we have 0.55. I think this should be 0.57, but this should be 575. Let me just find the value for that quickly. All right, so we go back and we see that in the middle of this and the middle of 60, 55 and 60, we have 57.5. You can go ahead and check that. So this would be 57.5. And right here, we just spoke about it, right? In the middle of 40 and 45, we have this guy right here. So no, right here. The middle would be around here, this section, right? This will be 42.5. So the value actually falls right here. So this will be about 43. Remember, it's just a simple estimate. So it's not really anything to worry about, really. You're just estimating. So are we understanding the position so far?
Yes, sir.
All right. Any questions before we move on?
No, sir.
Okay. So this should be 57.5. Let me just do that quickly. 57.5, 0.575 minus 0.43. Right, we get 0.1145. Right, 145. And 0.7 divided by 0.145 is 5.17. All right. So we plug in our values. We have our y2 values, we have our y1 values, our x2 and our x1, right? We quantify this by minusing 0.5575 minus 0.43. We did the same thing up here, and we simplify this down, and we get 5.17. That is our final value for the gradient. So we have now calculated our gradient, right? All right. Let me hear a yes, sir, or no, sir. You want me to go over it again? All right. So I'll take that as a yes. Any questions? All right. All right, let's move on then. All right. So since we're good so far, right? Remember, we remember this, right? This is just a definition again. We're bringing up back that definition. All right, so we'll go to the units now. This is very simple. We have our units. Now, our gradient, if we want to calculate our gradient, remember our formula is y equal mx plus c, right? I forgot to mention that look on this graph right here. Remember that this is the same graph as this, right? So what would our y-intercept be for this graph? What would our y-intercept be for that graph, particular graph? Anybody want to give it a try?
Zero.
Right, 0. Thank you so much. Thank you so much for that. So that would be 0. So our y-intercept would be 0. And our formula states that y equal mx plus c and c is equal to 0. So therefore, y equal mx. Now, if we want to find m, which is our gradient, m is representing our gradient, how do we calculate this? What do we do? What do we do here? We want to get m on one side alone. What do we do? Anybody?
Sir, you carry the X on the other side where the Y is.
So how would you do that? Right. Perfect. But how exactly would you do that?
You carry it over.
No, like
Like divide it like so.
Divided
right.
by
You
y.
divide both sides by x. right? So if we divide this side by x and we divide this side by x, these x's are going to cancel. So we're going to be left with y over x equal m, right? Now, if we remember this, our same graph, we're working with that same graph, and we said that y is period squared, right? Period squared, which is t squared, right? Remember this? And this is our L. Now, the unit for L is of course meters, right? Unit for length is meters. And the unit for time is of course seconds, right? Seconds, right? Sec. This is moving a lot slower today, right? And then because this period squared, it would of course be second squared. So it is not difficult. We're just finding the unit for this right here. This guy right here. The unit for the gradient. So calculate the unit for the gradient and we get seconds squared over meters, right? And m is of course in the denominator. So it would be a -1, right? Whenever we have a unit in the denominator, right, it is essentially -1 and our second squared. Second squared m to the -1. Are we understanding so far? Are we get that?
No,
No,
sir.
sir.
No?
No, sir.
Right. So we said that this is our formula, right? M equal y over x. Now from our graph, we see that on the y-axis we have period squared, and the unit for for squared is seconds, right? The unit for the period is seconds. So the unit for the length is m, right? And if we're going to square the time, it would be seconds squared, right? Are we understanding that? We get this right here. Are we getting this? The unit for time, seconds, and the unit for length, meters. Is that true?
Sir,
Hmm?
me not understand no way right now.
You're not understanding?
Nothing.
All right, no problem. Let me rub this out.
So sorry, I can't type it.
It's in the presentation form now. It's going to be difficult to type. What is the same thing we have right here? I'm just showing you that for it's the same thing we have right here. We have it already here. That the unit for time is seconds. Agree?
Yes, sir.
And the unit for length is meters. Agree?
Yes, sir.
Right. So because meters is in the denominator, we have a -1 here. That's why. Because we want to place them in the same, right, in the same position. So we just put a -1 here to indicate that it is in the denominator. And we still have our seconds squared. But because it was period squared, it cannot be just seconds. It has to be also seconds squared. You understand now?
Yes, sir.
All right. I only hear one person.
Repeat the part about the
Repeat,
T
please.
square part, sir.
T squared. All right. So from our graph, we have period squared, which is time. It's essentially time, right? The time it takes to complete one oscillation. Period squared, right? So I have a message in the chat. All right, I am confused. Okay. We will All right, let me just say this one more time. Bear with me, right? So we have period squared, which is essentially time. It is basically time it takes to complete one oscillation, right? Time squared, and the unit for this is seconds squared, right? The unit for time is seconds, right? So the unit for time squared would be seconds squared. Are we getting that, Mr. Brown? You understand a message in the chat? The unit for time is seconds, right?
Yes, sir.
All right. And the unit for length is meters, right?
Yes, sir.
Right. So we have seconds squared and meters. We have seconds squared and meters. And we have seconds squared in the numerator and meters in the denominator, because the second squared is from the y-axis, y over x, and the x-axis we have length, right? So it is essentially meters. Are we getting that? Are we getting up to here, up to this point?
Yes, sir.
Yes, sir.
No, the final thing is just we're just rewriting it so that it looks presentable. So we have m, and we want to get it in the same line, right? This line right here. Realize that there's no denominator, so we just put a -1 to indicate that it is in the denominator. It was down here, and we move it up. It has to be in a -1 position. That's better.
Sir,
Go ahead.
sir, basically say y over x, so y would equal, because I period that, so it would equal time, and
Right.
the unit for time or the seconds, and
Right.
and the x, I unit feet length, so you put meters did it, and then you just
Right.
write it in a presentable way.
Right. With the -1 here. Okay. If you're having trouble, this video has been recorded, so you can watch it over, right? You can watch it over, and if you're still having trouble, all right, not a problem. Right. No. We move on to the simple pendulum. We want to calculate. Just bear with me for a second, right? I know this looks scary, right? But just bear with me. This formula will be given, right? For example, remember we're going over the content for the labs. So when we start doing back labs again, when we start doing back labs, we are going to be doing this in the lab, and you'll be given everything that is here, right? And this is also in the activity. Some persons went ahead and already calculated the activity due to gravity. Right here, a question. Mm-hmm.
So you mean over school?
Yeah. So we're arranging for you to come and complete the labs. The point is, if you can't complete the labs, you cannot do physics. That's just it, right? So that's just the reality right at this point. If you don't want to leave your house, I'm sorry, you can't do physics. You have to do your lab.
Sir, we never said that, you know, sir.
I'm troubling it.
I do physics because of part of my job line.
Okay, no problem. I'm just messing around, right? So this will be given to you. Right? You don't need to be scared, right? But it's just a relationship between the time and the length, and it backs up the fact that as the time increases or as the length increases, the time also increases, right? We'll do more of this when we do Hooke's law, right? But time is against us. All of this will be done. I just wanted to show you, for those who wanted to see, this is our final product. This should be pi squared. Right, a little error again, right? You don't need to worry about all of this. All of this will be given, right? And you will have these in the notes. You won't need to know to show this. You're not required to show this. You just need to know this final product.
Sir,
Question.
all them are the on the activity.
As I said, you'll be given this, right? You'll be given this. You don't need to worry about this up here. You don't need to worry about that. right? You'll be given this. You will be given this, right? I'm just showing you that we have t squared on the y-axis. We have m, right? Our m here. This is our m. This would be our gradient, and this is our x. And remember that c is equal to 0. That's all. Don't need to worry about it. If you don't get it, it is okay, right?
Sir, question.
Question.
Is C always equal to 0?
No, it depends on the graph,
Oh,
right? If the graph is here, C would be equal to 1, right? So we have our gradient, right? G, we have m. Remember, where m is equal to 5.17. We calculated that around here. We calculated this. This is 5.17.